From the review or from the survey, it seemed like kids were most interested in learning about gas exchange. And so that's what this PowerPoint is going to be about. Gas exchange takes place in a couple different ways. You have external respiration, and think of that as exchanging gases with the external environment. So it's exchanging gas between the alveoli and the blood. So breathing in oxygen, oxygen going into the blood, carbon dioxide coming out of the blood. Internal respiration is gas exchange happening inside your tissues. So it's oxygen leaving the blood, going into your muscles. CO2 leaving your muscles, going into your blood. And then cellular respiration, back in biology, remember cellular respiration happened in the mitochondria, and that's where we make energy in the form of ATP. So cellular respiration is using that oxygen to break down our food molecules in order to make energy. So the major function of the respiratory system is to supply oxygen to our body's tissues and then to get rid of carbon dioxide, because CO2 dissolves in water to make acids. And so we don't want that acidity in our system. So of course, it's all driven by diffusion. And we mentioned this, I think, on the first PowerPoint. Just a review of diffusion from biology, it's things moving from a high to a low concentration. So where there's a lot of oxygen molecules, it'll move away to where there's just a few oxygen molecules, right? And CO2 does the same. In this chapter, we think more of gases and pressures. So it's moving from a high pressure area to a low pressure area, and it's referring to individual gases. So oxygen will move from its high pressure area, which is because it has a lot of molecules in a space, right? So it's directly related to its concentration, but you would talk about its pressure gradient rather than its concentration gradient. So in the capillaries, in the lungs, remember capillaries, the one cell layer thick vessel, that's where gas exchange is happening. So oxygen is going to go into the blood. The arrow down is from the capillaries, and then this is going into the blood. And then CO2 will leave the blood. And then in the lungs, you're going to pick up oxygen and you're going to drop off CO2. And then here, this is at the body system, the blood is going to deliver oxygen, so it's going to lose oxygen and pick up CO2. Okay, so diffusion rate, anything that affects diffusion rate will also affect gas exchange. So some things to think about: temperature. Remember, molecules are moving more quickly at a higher temperature, which means they're colliding more often, which means they're going to spread out more quickly. So increase in temperature increases diffusion rates. Pressures, so as you go down underwater, like every 30 feet, you're increasing an atmosphere of pressure. So you're going to, as you dive deeper and deeper, go through gases more quickly. And the opposite would be true if you're climbing a mountain. As you go up, you're losing pressure, and so gases won't diffuse as quickly. That's why you get lightheaded at high altitudes. Surface area also helps in the diffusion. We said in this unit, we talked diffusion by way of pressure rather than concentration gradients. So partial pressure, if you've heard of Dalton's law, the pressure of an entire gas is equal to the sum of the partial pressures of each individual gas. And that makes sense. Like if these three, A, B, and C, are going into if these are the, we only have A and B, sorry. If A and B are part of a whole gas, the pressure of A plus the pressure of B is going to equal the gas pressure as a whole. So if this one is 300 millimeters of mercury and this one is 400 millimeters of mercury, then together they make 700 millimeters of mercury. So this is one of our gas laws. And if we were in class, we would definitely be doing some math with this. And this formula would be on your test, and you'd have to do some math with that. This week, I'm giving you a choice board, and you can choose what you want to do for your activity. One of them does use the gas laws and does some math. Okay, so this is going to be relevant because the air we breathe is not all oxygen, right? The air we breathe is a mixture of gases. About 78% of it is nitrogen, approximately 21% is oxygen, and less than 1% by quite a bit is carbon dioxide. This number is increasing. We're getting closer and closer to 0.04 with our atmospheric gases. And then just under 1% is rare gases. Now, the only two that we really care about is oxygen and CO2. Nitrogen does become a narcotic at depths under 100 feet. So, like this isn't going to be part of our respiration, but this gas will build up. And because you would be under 3 more atmospheres of pressure, this would really be pushing the gas into your tissues. And so sometimes people get kind of drunk on nitrogen at deep depths, and they think they're scuba man. They think maybe they could breathe underwater. But we don't. For our purposes, we're just going to be talking about oxygen and CO2. So those pressures are going to be relevant to us. So a typical, like where we're at, we're under 1 atmosphere of pressure. So if this is Dalton's law, it doesn't matter what volume I'm using because it's on both sides of the equation, right? I'm going to use 1 atmosphere that's where we're at, and 1 liter just to make easy numbers. So these numbers here, 78% of my gas is nitrogen, which means its partial pressure is 0.78 atmospheres. And so this is what we're looking at in our bloodstream, 0.21 atmospheres coming in. So if that is a higher pressure than the oxygen pressure in our blood, oxygen will move into our blood. If it were lower than what's in our blood, oxygen would move out of our blood. So we can assume this partial pressure is lower in your tissues than it is in the blood. And so it moves into the tissue space. Okay. So that's governing the diffusion. Now, oxygen is carried on hemoglobin, and we talked about this, I feel, a good amount when we were in the blood chapter. So now we'll just talk about how oxygen is affected by temperature and pH. So this is our hemoglobin molecule. Remember, it had 4 heme groups, iron, and each of those iron bind oxygen. So it can reversibly bind oxygen, which means it can release it, which makes sense. In order for our tissues to get oxygen, hemoglobin would have to release it. So some of the oxygen may dissolve in the blood itself, but the majority is going to be bound to the hemoglobin molecule. So here is a couple things to think about with that. So in 100 milliliters of blood, approximately 20 milliliters of it will be oxygen, which means the partial pressure of oxygen coming out of the lungs will be at 20 millimeters of mercury. And as you go through the system, and like each of the things you guys can choose on the choice board uses a different piece from this lecture. So one of the worksheets deals with the partial pressures, and you would want to look at the numbers, and you would expect it to start high, and then the partial pressure is going to be low after it leaves the tissue spaces, right? Because it's going to drop off oxygen. So there's where we said the majority of it is tied to the hemoglobin molecule. CO2, on the other hand, the majority will be tied up in a compound called bicarbonate. So that's a buffer. It can release CO2 if we need more acidity in the blood. It can tie up CO2 if we need to make our blood more alkaline. So here we go with CO2 diffusing into our bloodstream. 7% stays in the plasma. The rest of it will enter into the red blood cells. And then it's going to be some bound to a hemoglobin molecule, and the majority, will be bound in that bicarbonate ion. And we're going to talk more about that bicarbonate. And that is our acid-base buffer for our blood. Okay. So this is that bicarbonate. This is carbonic acid. So when CO2 combines with water, it makes an acid. That hydrogen can be released if the blood is too alkaline, making the blood more acidic. So even though carbonic acid is an acid, it's a weak acid. So this is more alkaline in the blood than when bicarbonate is dissociated and the CO2 is alone in the water and hydrogen ions are alone in the water. So that makes it more acidic. 2 things that can affect, I see that carbon dioxide, I'm kind of going back and forth between oxygen, and I didn't mean to do that. I meant for all the CO2 to come after this. But this is oxygen, okay? So This is Bohr's effect, and it happens. So here we have pH, and remember, the lower the numbers, the higher the acidity. So 7.2 is kind of as acidic as you would want your blood. Not acidic. That's like, we're going to range between 6.8 and 7.2 probably. So we can see this is oxygen, how much oxygen is tied to hemoglobin. At lower pHs, where it's more acidic, hemoglobin will release oxygen. And I'm going to go to another slide and explain why that makes sense. Same thing over here, temperature. With higher temperatures, hemoglobin will release oxygen. So it doesn't have as great an affinity. And this would make sense to you. Think about when you're exercising, your muscles are generating heat, right? If I'm exercising, I'm probably going to need more oxygen, right? So this is a good like mnemonic you can use, is just think about your body being active. When you're active, you're hot, and you're thankfully hemoglobin releases oxygen, because when we're exercising, we need more oxygen anyways. So that explains the temperature effect on the Bohr shift. And then this explains the pH with the same thing. When you're exercising, you're producing CO2. CO2 makes your blood more acidic. So doesn't it make sense? If I'm active, I need more oxygen. So again, hemoglobin releases oxygen when the blood pH is more acidic. So those are both the Bohr shift. So far, so good? Okay, so we talked about carbon dioxide, and we're going to keep going with that and how our body regulates the CO2 in our blood. So we, first of all, use that bicarbonate, and this is what it's showing you. The bicarbonate can dissociate. We can have carbonic acid, which is a weaker acid than hydrogen alone, or we can form the carbonate ions. And so whatever your blood needs, it's going to either donate hydrogen or release hydrogen. And this is just a reminder that the more CO2 you have, the more acidic your blood is. So CO2 combines with water to make carbonic acid, and that lowers your pH. So what happens, we're going to, like CO2 is your #1 factor that controls your breathing rate. You would probably think oxygen, but it's not. Oxygen only comes into play when it's extremely low. So your everyday breath is governed by the amount of CO2 in your blood. And that's because of the pH. And we have baroreceptors in our carotid arteries that that's the one going up in your neck and in our aorta that measures the partial pressures of those of the CO2 or of the oxygen. So when the body needs to rid itself of carbon dioxide, you're going to breathe more quickly to get rid of that CO2. And if you need to let CO2 accumulate, you'll breathe more slowly, and that'll give it a chance to build up. So again, in the worksheets, you might have chose to do some biozones, and it's going to investigate this a little bit. The respiratory control, remember, is in our medulla. We learned that in the brain chapter. So when oxygen levels are really low, this baroreceptor in the carotid artery will send signals to the medulla, and then that will tell then your medulla will send signals to the lungs, and you'll have a reflex reaction that causes you to breathe. So CO2 levels are the key controlling factor of breath. One of the choices you have in your choice board today is a number of different types of labs. So you might choose to do a lab where you're holding your breath, or you're hyperventilating, drinking water, singing, all different things that change how you breathe. And remember, like if you're holding your breath, it's not that you need oxygen that causes you to breathe in, it's the accumulation of CO2 that causes you to breathe out. So it's interesting, pay attention when you hold your breath, if you first breathe out or if you breathe in, when you feel the need to breathe. Okay, so acidosis, typically things speed up, like all of your body processes will speed up when your blood pH is too low. And that is called acidosis. So under 6.8, you're gonna be convulsing. So that's the extreme. So that's gonna help you remember that breathing rates are gonna speed up, and the whole purpose is to get rid of the CO2 that's causing your blood to be acidic. And then the opposite, alkalosis. So typically things slow down during alkalosis. 7.4, we're going to be going into a coma. So that's the extreme. So all the body processes are slowing down, including breathing rate. And so we slow our breathing rate down in order to let CO2 accumulate. And so that's going to bring our blood pH back up to the normal. So this is a great example of homeostasis and negative feedbacks. And then releasing the oxygen. So now we're getting, you know, the blood is getting back to the alveoli, and it's again being governed by that partial pressure. So the CO2 is going to be at a higher partial pressure now than the alveoli, because there's more blood, there is more CO2 in the blood than there is in the air we're breathing in. Remember, that's only 0.03, very little. Okay, so then the hemoglobin will release the CO2, or the bicarbonate will dissociate and release CO2 and water. So then the CO2 will be able to dissolve out of the red blood cells. Good with gas laws? We're almost done. Okay, the last one, we really already talked about this one, but I didn't give you the name, so I wanted to hit that for sure. Boyle's law. That is the idea that volume and pressure are inversely related. And that should just make sense. These are all gas molecules, right? So as we add pressure, what's happening to our volume? It's getting smaller. So, I mean, you can think of anything you squeeze, right? When you squeeze something, you're adding pressure, and it's going to get smaller and smaller and smaller. So this is in large volume, low pressure. Things are very far apart. This is a high pressure, small volume. Things are really close together. So that's going to create that high pressure concentration gradient that causes air to move out of one area or the other. So this is really important, not just for internal respiration, but external respiration. And I'm going to show you a video. We talked about how this is like 1 minute, don't worry. The diaphragm drops down and the thorax will rise, increasing the volume, and air comes in. So why is that? Because when you increase the volume, the pressure got very low. So now the pressure is lower inside our body than it is outside of our body. Air comes in. And then we talk about the diaphragm will move up, the thorax will come down, really decreasing the volume. So here we have a very small volume, high pressure. So things moving from a high to a low pressure will move out of the body because it'll be higher than the air. So this is just showing you that difference in size. So you can see an increase in volume and a decrease in volume. So when you breathe in, it's because of a low pressure, air like passively moves in, and then an increase in pressure causes air to move out.